In this section, we're going to discuss how to find the projection of a vector on a vector, because earlier we found projection of a vector on a line. So you will realize that there's not much difference. So I'm going to define it like that. Okay, the projection of the vector on another vector is actually the same. Is defined as the projection of the vector A on a line that is parallel to B. So I don't care where B is pointing. Basically, it is the same as the projection of A on a line parallel to B. So earlier we found how to project a line, a vector on a line. So if you see diagrammatically, it looks like this. First, step one, I will draw a line like that, parallel to B. So I actually really don't care what is B, what is the direction of B, but I just draw a line. Step two, the projection of A on B is actually the same as the projection of A on the line L. So the arrow actually follows the arrow of A. So remember, it's almost like casting a shadow perpendicularly, or rather cast where we are sun rays and then cast a shadow downwards. So now that we know this definition, we want to learn how to find it using the concepts we've learned in vectors. So I'm going to show you how to find it. How to find it. Let's break it in two cases. One, theta is acute. What do I mean by theta is acute? Means this. All right, I have a vector A. All right, I want to find the projection of A on B, where theta, which is the angle between A and B, is acute. I break it up first. I assume theta is acute. Later, I'll deal with the case where theta is obtuse. So now, if theta is acute, this is exactly how the diagram will look like. Okay. Then can I then safely say that the length of CF, just the length of CF, the absolute value, this length, all right, this length is A modulus of A cosine theta. Okay, I'm just going to I know you all are more familiar with, if I draw cosine theta, where theta is acute. Let's bear in mind theta is acute. Cosine theta is adjacent, which is CF, over hypotenuse, which is modulus of A, which is this one. All right, so therefore CF is just A cosine theta. Now, then we also realize what is A cosine theta. Now you also have to recall A dot B is actually mod A mod B cosine theta. Right? This definition. And therefore, let's divide both sides by modulus B. Divide both sides by modulus B. What do I get? I get mod A cosine theta is A dot B divided by modulus B. And actually, this one, beg your pardon. All right, this one is actually unit vector of B. So no problem. All right, so length of CF is actually A dot B hat. And I would just want to emphasize that, I erase this. I just want to emphasize that cosine theta here we are dealing with, theta is acute, therefore cosine theta is positive. Right? It will confirm be positive because we are dealing with the case of theta being acute. So CF is in this same direction. So this is positive number for sure. All right. Then what is actually CF? What is actually CF? Now, recall vector A is the magnitude of A times unit vector A. Correct? Yes. Suppose if I tell you A is in the direction, suppose our example 1, 0, 0, and has magnitude 5. Then for sure, since this is a unit vector, so A must be 5, 0, 0. right? So since that is true, since I already know the magnitude of CF, so CF hence will just be magnitude times the unit vector. Scalar product, so it's not scalar product, scalar multiple, then times the unit vector B, because this is the direction of CF. CF must surely be in the same direction as B. So here we have shown just by trigo, all right, that CF, which is the projection of A on B, is just this. You may want to replay the video to understand this again. Next, what if theta is obtuse? If you contrast this, if you replay back a little bit and you contrast this diagram with the earlier diagram, there is a difference whereby your theta here is an obtuse angle. Now, I deliberately write this result here. We're about to prove that regardless whether the theta is obtuse or acute, the result will still remain the same. Okay? You will likely forget this proof. Likely. But it's fine. But I want to prove it once so that I want to show to you that it doesn't really matter. Okay? So let's do this. Let's take a look at this triangle ACF. Okay? This ACF triangle. Since this is obtuse, this is your triangle here. Okay? Cosine alpha is actually cosine 180 minus theta. All right, and you know the second quadrant is actually negative cosine theta. So far so good. Now, if you take a look at this triangle here, CF, length, I'm talking about length of CF. Length of CF here, again, I use the idea mod A cosine of this acute angle, which is actually negative of mod A cosine theta, because as we've shown earlier down here, which is actually negative of this, the same process that we have done earlier. So, but I don't just want CF, I want to find the vector CF. Ultimately, I want to find what is CF vector. It is actually the magnitude times the unit vector. Correct? And do I know the magnitude? Yes, I know the magnitude. The magnitude is this one. Right? The magnitude of CF is this. Do I know the unit vector? Let's bear in mind the unit vector of CF is this one is not B hat. Why? Because they're in opposite direction. So actually the unit vector of CF is not B hat, it is actually negative B hat, because it's this CF is in this direction. So I'm going to show now. All right. So it is actually the magnitude, which is this one, times the unit vector, which is negative B hat. In the end, you realize the negative becomes positive. It will end up with this result here. All I'm trying to say here is that no matter whether A and B forms an acute angle or an obtuse angle, you will get this same result.